Good morning. My name is Andre Rosso, and we're going to be looking now at the third module, so Module 2, which deals with the data center environment. Here we'll be looking at a number of different topics. You can see the objectives and the topics listed on the slide. So the core elements of a data center. So Joe already mentioned some of those. Virtualization of an application and the host layer. We'll also look at disk drive components and performance, obviously very important in the storage environment, which is what we're typically interested in here. We'll look at host access to that storage through direct access, so the way we can connect hosts directly to the storage without the use of sharing done via a storage system. And of course, we'll also look at one of the newer technologies, the use of flash drives and some of the benefits that they give us in a storage environment. So we'll start with Lesson 1. And Lesson 1 deals with applications, the database management system, and the host or the compute environment. The topics here include applications and application virtualization, the database management system or DBMS, components of the host system, and compute and memory virtualization. So let's get started then by looking at applications. Well, applications, of course, are the pieces of software that do the work. And for the most part, although we are aware that there is an operating system running on the hardware that we're dealing with, we're interfacing with the application itself. You're usually not as concerned with the fact that you're running, let's say, a Windows environment than that you are running a specific email program, because that's how you communicate with everybody else. So the application then is important because a lot of the focus in the environment is on applications. What do they need in terms of storage? How do we use that storage? What are the performance requirements and so on? So this is really a very important part then of the data center. And of course, notice it provides the logic for computing operations. So this allows us to do work which is useful. Now, what are the commonly deployed applications that we might find in a typical data center? Well, there are a number of them. You'll see a range listed here, but there will be applications related to the business itself. So things like email, which of course has become increasingly important in modern business. Enterprise resource planning, things like customer relationship models, all that type of thing that relates to the way the business runs and how we make most efficient use of those business resources. Additionally, we see something like management applications. Again, so the management of the resources that we are using in the business. Data protection, if you use a laptop at all that has been assigned to you by the company, you will notice that there is antivirus software running on it. So of course that type of protection really very important, ensuring the integrity of that information, and of course the fact that it is secure, that only you can access it because of the way we implement usernames, passwords, and so on. So that security then, one of the vital components, as Joe mentioned earlier. So a wide range of different applications are important to us in the data center environment. Also, when we look at these applications and we look at them from a storage point of view, there are certain characteristics that are going to be important to us and things that we really need to know about those applications in order to plan properly for them. And those include the things that we see here. So 3 different areas listed on the slide. First of all, is the application read intensive or write intensive? What we're really interested in is the mix between reads and writes. And this will become important later on. We'll be looking at RAID, and we'll see that in some circumstances, writes are very expensive in terms of the overhead and the potential performance impact that they cost us. So we need to know what that mix is going to be, the number of reads and the number of writes. We also want to know how we access that data. And in this case, how we access it, meaning either via some kind of sequential mechanism or via a random mechanism. So what is the difference between those? Well, in a sequential environment, as we make new accesses, the addresses associated with those accesses are going to increase, typically rather than decrease, but they will increase, and they will increase without any gaps in them. So if my first access is to block number 0, and my second is to block number 1, and my third to block number 2, then I'm starting to see a sequential pattern. And of course, as we'll see when we look at disk drives, the more sequential that access is, the better the performance that we can expect to see from the physical disks. So a lot of what intelligent storage systems, another area that we'll be looking at later, will do will be to try and make the access as sequential as possible in order to make best use of the underlying hardware, which of course will be the physical drives. The opposite of sequential then is random. And with random access, what we're doing is accessing data that really is accessed with no pattern discernible in the addressing of that data. So we'll be jumping around all over the place from high addresses to low addresses, or high locations to low locations. And again, when we look at the underlying hardware, the physical drives, this is not very efficient, because we have to move components like the read-write heads. Again, we'll be looking at the structure of a disk in the not too distant future. But we have to move certain mechanical objects around, and that takes a finite amount of time. And that time, of course, taken in moving, reduces the amount of work that can be performed. So we really are vitally concerned about the difference between sequential and random. Another area where this is important is when we look at replication, because replication typically will involve, firstly, writes only, so we don't normally replicate data that is read to a remote location, only when it is written, but also data that's written randomly causes a lot more overhead on most systems than data which is written sequentially. So we really need to know that about the data. And of course, finally, we want to look at the I/O size. We know that we're seeing a certain number of reads and writes and that they are either random or sequential, but how large are those I/Os? And again, if we have lots of small I/Os, the underlying disks will behave very differently than if we have a smaller number of very large I/Os. Because obviously large I/Os are typically treated as if they were sequential, because they will be, whereas smaller ones might and often are random in nature. So really important areas to know about an application, to know about the behavior of that application. So we've had a look already at some of the definitions of terms that will be used, and here's the next one, application virtualization. So here, that definition really is presenting an application without any dependency on the underlying computing system. So essentially, you are not making any assumptions about what is already there at the time that you allow the user access to that application. So what does that really mean? Well, that application then can be delivered essentially in an environment which is isolated. Again, the no dependency is one of the important areas that we're dealing with here. And what does that mean? Well, because we have the application encapsulated with everything that it needs, that does not already have to be in the environment. So we're not dependent, for example, on any specific operating system or any specific type of hardware, provided, of course, that what we have there is supported by the virtualization itself. And this really ensures the integrity of what we're using. So we've got everything encapsulated, so the operating system and the applications, and because we have control over that as one unit, essentially as one object, we know that there can be no changes made before it is delivered to the end user. So there's more control over the security, if you like, of that object and of that application. And then lastly, we can avoid conflicts that may arise between different versions of the same application. You may be aware, for example, that many applications will not allow you to, say, load version 5 and version 6 on the same hardware and on the same operating system. But if we can remove that dependency on the operating system, then it's quite likely that we can run multiple versions of the same software, of the same application at the same time. And we may need to do so. We may have, in any given organization, some requirement for a given version of an application and some other use which requires a different version. And normally, of course, that would mean lots of overhead. We might have to remove one version, load a different version in order to perform some work, and then perform the same thing or the same operations again to change back to what we were doing before. So this removes that dependency and makes it easier for end users to use those multiple versions at the same time. So how about database management systems? Well, Joe mentioned essentially what this is, and of course you gave some examples of a database management system. So Oracle was one of the examples, if I remember correctly, and SQL was another. So a database management system then, as its name implies, is going to be some way of managing databases. And databases, you've already seen, consist of structured data. So essentially, this will be, as Joe said, the data that can be organized easily into rows and columns. And typically, of course, the data in those rows and columns will be of the same type or refer to the same type of thing. So you might have a model of computer with a specific serial number assigned to a specific user. So you've got users in a column, serial numbers in a column, and the computer model in another column. So this then is structured data. And of course, the DBMS allows us to manage that. So it defines how that data is created, how it is organized, and how it is managed. And some examples here, of course, include the ones that we saw earlier. Now, importantly also, the DBMS is also going to determine how that data is accessed. And again, when we look at access, we're looking at what we're interested here in the storage environment. So how do we fetch that data from the storage where it is currently located? So the next area to move on to then is the host or server or compute environment. And obviously here we're dealing with the resource that will run the applications. So the typical server environment where you have a CPU, you have memory, and you have some type of I/O structure. So the capability to perform input and output from the system to the real world, where the real world will typically also consist of some type of storage. So a number of different examples are shown here, ranging from very simple devices. So you might have a tablet or even essentially a cell phone, although a tablet might be a better example. You don't have much in the way of external connectivity there. The tablet has its own memory. Of course, it does have a network connection of some sort, but everything that you do is on the tablet. You perform the input yourself by typing on a keyboard, either a physical keyboard or a virtual keyboard. It shows you the results of your operations on a screen. The data is saved internally, and of course, from time to time, you may need to access some external components, so you get things from the internet, for example. But all of those are built into that device. And of course, all of these other examples typically contain the same types of components as well. Now, the hardware itself is useless without something to run it, so there will always be an operating system of some sort. It may be very simple, it may be very complex, but there will be an operating system, and of course there will be applications that you will use to interface with that device, to allow it to do something that is useful to you. So what are those hardware components? Well, they've been mentioned already, but essentially in any computing system, no matter how simple or how complex, you can typically break it down into three different areas, and those will be the CPU, so the part that does all the calculation, the memory, the piece where you save all of the intermediate results and oftentimes the applications and so on, but again, that's typically temporary type storage, and then input-output. So that input-output will include devices that you use to speak to or get information from that system, so keyboard, mouse, screen, and of course will also include devices that perform external storage, such as disk drives or CD-ROM drives or whatever might be attached to that specific device. But the three basic building blocks then will always be the CPU, the memory, and the I/O structure. The software components then are those that are present to help the hardware do the useful work that we require of it. And the operating system has already been mentioned, but the operating system, of course, in many cases has a fairly difficult task in the sense that it must interface with a number of components which, although they may be of the same type or generic type, may behave in a slightly different way. For example, the operating system will allow you to save data onto a disk drive. But how many types of disk drive are there? There are a number of different manufacturers, all of whom may use slightly different command sets to allow that disk drive to do something. The architecture of that disk drive may be a little bit different, so the way the data is internally organized may be somewhat different. And the operating system typically cannot have all of the information that it needs about all of those devices. One of the reasons, of course, is that new devices are being added all the time, and the operating system cannot be updated frequently enough to include them. So another major component of software then will be the device drivers, pieces of software that allow the operating system to interact with the unique pieces of hardware that it has to deal with. And obviously, if you, let's say, have a system with brand XYZ disk drive, that is the device driver that you need. You don't need to have a device driver for all of the other types. So we can narrow it down and make it specific to that one particular piece of hardware. Also, we will have a file system and possibly a volume manager. So the file system will allow you to organize data and store it onto that storage in a way which is easy for you to retrieve. Essentially, the goal of the file system is really to remove some of the complexity of the hardware from you as an end user. If you want to store a particular file, for example, you just click on, say, File, and then Save. You don't have to say, well, this file is 4K in size, and I need to go and look at the disk drive to see which blocks are free, then determine that I have enough of them to save the file, then choose which ones I need and in which order, and then to do something like update a table that says this is where all the little pieces of that file can be found. So the file system does all of that work for you. And of course, it organizes the data in a specific way, usually with blocks of a predetermined and consistent size. So the volume manager then, and we will look at volume managers later, will allow you typically to do things with the physical storage devices. So we can take a group of physical devices and treat them as one logical unit, or we may take a very large physical device and be able to treat it as more than one logical unit. So again, that performed by the volume manager, which essentially deals with file systems but allows them to be used in a number of different ways. So the device driver then, as mentioned already, is essentially the piece that allows us to interface with specific components. So resides between the applications, which is where we interact, and the hardware, which of course is where the operating system has to interact as well. And this allows us then to essentially treat specific devices as though they were all of the same type. So again, the operating system will speak to a disk drive. And if there's a device driver there for the specific manufacturer's disk drive, it doesn't need to know that it belongs to manufacturer XYZ. All it needs to know is that if I send out a command to perform a head movement from one location to another, then the device driver will translate that into what is required for that specific device. Right, so again, it's virtualizing, if you like, some of that effort, taking away the strict requirement that we know exactly how this particular item of hardware works. Right, so the operating system then recognizes that specific device and can communicate with it in a way that it communicates with generic devices of that particular type. So the term virtualization has come up quite a bit. So what about memory virtualization? Well, memory in any environment is going to be a resource which has an upper limit. So there's only a certain amount of memory that you can use in a system because of, for example, a limitation on the number of slots you have for that memory. But there may be a requirement to do something that would overflow the available memory size. You may be trying, and Joe mentioned the spreadsheet earlier, so you may be trying to load a very large spreadsheet which could not all fit into memory at the same time. So what happens then? Well, the system has a way of using other storage as if it was memory and swapping the bits and pieces that it needs from that storage into memory as required. And of course, the most common other form of storage that you have available in systems will be disk drives. So we have the ability to swap areas of memory, typically referred to as pages, from the RAM, which of course has very fast access, down to disk, and then to take other pages from the disk and bring them into RAM where they can be accessed a lot more easily. So again, the system is automatic. You do not need to be involved with this, but you may know that it's working, because when you configure the system, you may have to set up something called a swap space. And when you set up a swap space, you're configuring the amount of space on this disk that can be used to swap areas of memory in and out. And of course, what that really means is that my system will allow me to see memory which is larger than the physical memory that I have. So again, using a laptop as an example, you may be constrained to say 4 gigabytes of memory because you only have 2 memory slots in the laptop. But you may at some point need to use applications that exceed that 4 gigabytes in total size because of the data they're accessing and so on. So the swap space that you have then allows you to behave, or allows the system to behave as though there was more than 4 gigabytes of memory there. And of course, it will swap pages in and out as required. Now, the thing to bear in mind, of course, is the access speed of that data, or of the data that we have stored in those different types of memory. When we look at the access speed of typical memory, so RAM, in a system, the access times there are measured in nanoseconds, so billionths of a second. So when you access that data, you know that the CPU is going to have it in a very short time. In disk drive environments, the access times that we deal with are typically in the millisecond range, so thousandths of a second, which is 1,000,000 times slower. So while the difference between a nanosecond and a millisecond probably doesn't matter much to us, because a millisecond is a very short time to a human, but to a computer system, a millisecond is a very long time. You can do an awful lot in a millisecond if you're running at several gigahertz. So that difference is very important. And we need to know then that once you start to perform swapping or paging, that the access time will slow considerably, simply because the drives are so much slower than the actual memory. And we'll see later, of course, that very same differential in speed is one of the reasons why in intelligent storage systems we use RAM, or regular memory, to buffer some of the accesses to data that is found on disk. All right, so again, we need to bear in mind that speed differential, which is about 1 million times. So the term logical volume manager was mentioned a short while ago, and I mentioned that we can, by using a logical volume manager, either, for example, take many physical resources and make them look like one logical resource, or do the reverse. Take one physical resource and make it look like a number of different logical resources. So here is the first generalized look at the logical volume manager. And as noted here, its goal is to really control the logical storage as seen by the host. So what does the host actually access? And of course, one way we can do this is by taking a number of physical resources, so the physical disks, combining them into a group of some sort, and then presenting that group as a single object back to the host. So in this example, we have 3 physical volumes. You can think of them as 3 disks. They have been grouped together. We create a single data structure out of those 3 disks, and it is presented as a logical volume then to the host. So the actual data, of course, is stored on those physical volumes. And there must be a translation mechanism that says, well, if I access a specific area on this logical volume, it means that I have to go to this particular physical volume and find the data there. And of course, the logical volume manager is going to do that for us. So we have the volume group then as the physical component. We have the logical volume as the logical component, and there has to be that translation between them. Now, if we look at other examples, so here in the leftmost example, you'll see that we have the idea of partitioning. So you are probably familiar with partitioning already. When you set up a new Windows system, for example, you may have a single disk drive, which could be very large. Let's say it's 1 terabyte in size. So you have an option. Do I want the entire 1 terabyte, for example, to be seen as my drive C? Or would I like to keep a part of it for drive C, so I know all of the operating system related information goes there, and then possibly create another piece where I can put all of my personal information? So that way it's easy to back up, because I know that this is reasonably stable. It doesn't change frequently, whereas my own information does. So I would then partition that hard drive into 2 pieces. And if I formatted those 2 pieces in a Windows environment, I'd probably call them drive letter C and drive letter D. So now I have the example where I took one physical resource, so a physical disk, and I divided it up by partitioning into 2 logical components, and those 2 components are visible then to me and to the operating system. The other example on the right-hand side really is an example of what we've seen already. So we can take physical components, we can concatenate them or join them together in some way. We can present them up to the host and to the operating system as a single logical unit. All right, so either partitioning large components into smaller pieces or concatenating smaller pieces to get one single larger object which we can access. Yes?
What are some common ways to combine multiple drives? Like in partitioning, it's pretty easy to understand how it separates, but what are some common methods for the other?
Right, so the question there is, what are common methods for combining multiple physical drives into logical objects? Well, a fairly common way of doing that is by using RAID. So again, we'll be looking at RAID in a while, but RAID allows us to group physical disks together in a specific way to allow, a larger logical object, which in fact may also be divided into smaller logical objects, but to allow some measure of protection and possibly improved performance at the same time. So that's a fairly common way of doing things. again, using a Windows host as an example, because that's what most people are familiar with, you'll notice that you can create, for example, striped volumes or RAID 5 volumes. And normally what you would want to do there would be to take a group of physical disks and to combine them to produce one large volume of a specific type. So that's normally what we do. Yeah. Okay. So the next area then that we look at is the file system. And this, of course, shows the flow of data all the way through from an end user right the way down to the physical drive. And of course, there are a number of layers, if you like, that we have to go through here, and a number of places where a bit of work has to be done by the operating system or by other components of the operating system. Specifically, what we're looking at here, starting at the user, is the user, of course, creates or manages a file. So in the example that I gave you earlier, you don't have to deal with all of the hardware and decide where that file is going to go. You know that you created a file and you want to save it as, for example, mydocument.txt. So we have a file that needs to be created there. Well, you've created data inside that file. You've given it a name. Where is it going to go? Well, the next layer down, the file system really is going to decide where that's going to go, right? You may choose, for example, a directory, but the file system knows where that directory is. So it's taken your data from that file, and now it knows it has to go to a specific place in the logical structure inside that file system. But how does that translate down to where I get to the physical disk drive? Well, the file system itself is keeping track of where I have little pieces of data, where I store those blocks. And as I mentioned earlier, those are typically small blocks or fairly small blocks, and they'll have a consistent size. So those may be, for example, 4 kilobytes each, and I would take my file and then determine where it can go in terms of those 4 kilobyte pieces. So I map from the file system to these file system blocks. But the file system blocks are still a logical construct. I haven't reached the physical hard drive yet, so where is that data going to go? So I go from the file system to logical volume manager extents. So I may have done something with those physical drives. I've concatenated them to make a bigger volume, or I've partitioned a larger drive to make smaller logical areas. So either way, the logical volume manager is going to say, well, those blocks on the file system have to go somewhere in terms of this particular volume structure. If I have 4 or 5 disk drives that make up my entire group, one of the things would be to decide which disk the data actually has to go to. So from those extents that are seen by the logical volume manager, I then map this down to physical extents, right? So I've got areas on the disk that I'm going to be using to store data. And those extents may be, and probably are, larger than the individual sectors. So the sector is the smallest amount of data that I can write to a physical disk. And almost without exception, that will be 512 bytes, right? So in some environments, it's possible to format drives differently, but normally it's 512 bytes. So I would take those physical extents then and say, right, these are the extents, the groups of sectors that I have. Where are the actual sectors? And I would then map that down to the physical drive and the individual sector locations on that physical drive. So from something as simple as saying, well, I want to create a small file and save it in a specific directory, we see that we've gone through a number of different layers that map that data in different ways until finally I get right down to the physical storage device and I determine where that data needs to go. And obviously, if I want to read it, essentially the opposite is going to take place, right? So I'm going to look at the file and determine, well, now I need to work out where I put it, then go to that location, fetch it, and feed it all the way back through to the user, making it visible as the file that the user originally created. Yes?
Does the LVM organize files like based on, they're all, let's say, .doc files or something like that, or what does it use as a mechanism for logically partitioning files into different categories?
Okay, so the question is, does the logical volume manager know about the file structure? And typically, no, it doesn't need to. The logical volume manager needs to know about where data is going to be stored based on where the file system knows about them. So the file system here knows about those files, and it will know whether it's a .doc or whatever it is, because typically that extension will be part of the file name or associated with the file name, and it will be saved in a directory structure which is under the control of the file system itself. But from there, you're essentially saying, well, if I've got a file system made up of individual pieces, where are those pieces going to go? And at that level, we don't need to know what file type it is at all. We really don't even need to know what file it is. We need to know, for a specific address, where am I going to map that all the way down to the physical disk? So no, it doesn't need to know about the specific file types.
Question.
Yes.
In Windows Explorer, the file manager, is it considered part of the OS, or is it like an application running on top of the OS?
Okay, so the question is Windows Explorer an application or part of the operating system? Well, essentially, it is an application, right? Because you can run Explorer as a separate entity, so it's explorer.exe, so it's an executable. And really what it's giving you is a view into the operating system. So you looking at where the data is, or the structure of the data, where it has been located at a logical sense, because you don't really go right down to the physical disks, but it's giving you a view into the logical structure. And essentially, it's an application. It's something that lets you see the structure of the file system.
Yeah, the reason I asked the question maybe to help understand the other person. For instance, if I am writing to a C drive, might be different than what I am writing to a mounted or mapped NAS share. Both of them I can see on the Windows Explorer, but the whole operation is going to be different. Not necessarily so different, but in case of the NAS, all the file system is going to be managed by the NAS.
Yeah.
In this case, in a local drive, Windows is going to take care of all this mapping.
Yeah. So a part of the operating system and logical volume manager working together are going to tell you where that data is, but essentially still from Explorer, you looking at the structure of that data, and you choose to save it in, as you mentioned, either like a local drive or something that you have access to across the network, so a share. But to you, it really doesn't matter. And to Explorer, it really doesn't matter either, right? So you're just saying, I want to save it here. But underneath that, the other components here, so the volume manager and so on, they are going to need to know where that data needs to go physically. Yeah. But yes, the access and the saving of that data to those locations will be different, but not at the level that you're really dealing with it at the Explorer level. Yes.
So is it necessary to create redundancy? I mean, is that like a single source of failure for finding your information if the mapping structure goes down?
Okay. Well, all right. So the question is the structure, for example, the mapping performed by a logical volume manager, is that a potential single point of failure? And essentially, yes, it is. The one thing that in many cases you cannot recover from in any host environment is a failure of the operating system, right? So the operating system might crash, and that means that at that point you have lost access to everything, to all of your data. You're not necessarily lost the data itself, but you've lost access to that data. So from that point of view, yes, it can be a single point of failure.
Is that something you back
Right, so the question here is that part of what you would back up? And yes, that information about where the data is stored is all part of what is saved to the physical disk. So all of those structures, like your directory structure and so on, are all saved on disk, which is why if you power down your laptop, when you power it on again, all the files are still in the same place and you can access them in exactly the same way because that structure is saved there. So the backup would save that structure as well, and if you needed to restore it, you'd get that same structure back. So in terms of long-term preservation, yes, absolutely. In terms of short-term protection, though, aside from doing something like clustering and so on, there's really nothing that you can do about that really being a single point of failure, because the software always will be. There's normally redundancy built into hardware, but it's very difficult to do the same thing on a single host with the software. So yes, that is a single point of failure. Yeah, you'd be saving all of that information.
If I understand you right, if you lose data, it just tells you where you lost the data, right? It gives you an address. You'll have it mapped logically to a volume, a size for that, appropriately sized for that volume. That's all you'll know at that point. If you do lose the data, is where it was lost. Is that right?
Well, sometimes you may not even know. If you do lose data, you may not know where it was. So there are a number of ways in which you could lose data. Most commonly, though, if the data has already been committed to a device like a disk and you lose it, it's because it has been erased in some way or it has been corrupted in some way. And then typically, let's say it became corrupted, the file system would know where that particular area of disk was used inside a file. So the file system would know, like, that's where that particular piece of data is, but you may not know. And you may not be able to access, that particular file. So sometimes, you wouldn't know at all.
That was my question now.
Okay.
At that level of abstraction.
Yeah.
The user may not care, but the LVM would know the address where it was lost.
In many cases, yeah. Because, again, if you see like corruption of some sort, it's the data that has been damaged in some way, not the location or the information about where the data is. Although obviously part of the data structure would be, let's say, the directory type information, and if you damaged that, you might not be able to find where the data is either. So again, it's not an easy. Yeah.
That's what I was kind of getting at.
Oh, okay.
Address versus data.
Okay. Yeah. So if you lost the data structure or the information about the data structure, yes, then that could be an issue. But typically, of course, structures like the directory will be kept in more than one location. So you wouldn't only have one directory area, which would be a single point of failure. There'll be a backup copy made somewhere else, so that if you see something has become corrupted, you can go to the other structure and try and find where your data is. So, yeah, there are methods to try and ensure that that doesn't happen. Yeah. Okay, so that then a look at how we, from an end user point of view, map the files that we create all the way down to the actual physical storage. So the next piece that we'll look at then is compute virtualization, and the compute here, of course, being the server itself. So server virtualization or compute virtualization means abstracting the physical hardware and potentially allowing multiple operating systems to run concurrently on either a single host or on clustered hosts. And again, in a single host environment, we potentially have a single point of failure, so clustering would be used to try and improve the availability of that system. So availability, again, one of the things that Joe touched on earlier. So if we look at this, notice that in this particular environment, we have the hardware, so at the base layer, and of course the hardware includes all of the components that we see here. So that would be the CPU, the memory, and those I/O devices. So all of the things that allow us to communicate with the external world, for example, the network cards, and of course the hard drives to allow that data to be saved. And on top of that, we would have the abstraction layer itself, so the virtualization layer or the hypervisor. And you can think of the hypervisor as being an operating system which allows access to those hardware devices by virtualized hosts found on top of it. And those virtualized hosts are virtual machines. So the hypervisor then is essentially an operating system, but a very small, very efficient operating system which allows very fast access to all of the hardware. And it has to be very fast because you're allowing multiple hosts, essentially those virtual machines there, access to the same physical components. And you need to be able to switch between them very quickly as they require access to those components. So the advantage, or one of the advantages here, is that we can run multiple operating systems at the same time. So we could be, for example, here we have the x86 architecture. We could be running Windows and Linux, for example, at the same time on different virtual machines, but on the same physical hardware. So that virtualization layer then controls, as I mentioned, access to the physical resources from those virtual machines. And of course, there will be a mechanism in place to ensure that they all get a fair shot at using the resources that are there.
So I was wondering about the capacity. At some point, would these virtual machines no longer be able, it's using up whatever capacity is there and resources, or is this just, it can't be infinite, but it goes on and on?
Okay, so the question there is about the resources themselves. Well, the resources, of course, always will be limited. So what would be the simplest? Memory is probably not a good idea. Let's say CPU. All right, so you have a CPU, it's running at 3 gigahertz, let's say, and I have 3 virtual machines there. Depending on what those virtual machines are doing, because obviously if they're idle, they're going to need less of the resources than if they're running very hard, performing a lot of work. But essentially, the total of all of the CPU cycles used by those 3 virtual machines will not be allowed to exceed 3 gigahertz. So if you continue to add virtual machines to this environment, you're going to run into limits. The limit might be the amount of memory you have, or simply the amount of CPU power, or even the amount of storage, or whatever else it might be. But there will be upper limits. And at that point, because you've hit the limit of a resource, you will see things start to slow down. So either all of your virtual machines start running a whole lot slower because there's not enough CPU power, or you see the memory access slow down because there's not enough memory, we have to start swapping, or possibly you don't have enough storage at all and you run out of disk space, so you can no longer save all of the files that your users are creating. But definitely there is an upper limit, and part of the design for environments like this will be to say, well, what do I have at the virtual machine level? And to take all of those, essentially aggregate them together and say, this is what I'm going to need for the hardware that will be accessed by those virtual machines. Yes.
So is this provisioning and management of the virtual machines, is this managed at the virtualization layer? Is that where you get the view as to the capacity and the limitations of the hardware that you're running the virtual machines on?
Typically, the management application that you're using is going to give you really a look at what's happening at that layer, yes. So how the CPU cycles are being split up between the virtual machines, how memory is being allocated, and so on. Yeah.
Is that part of the OS? You mentioned like a small and efficient OS at the management or at the virtualization layer. Is that part of it?
The management is normally a separate application. So again, in the let's say the VMware world with ESX or ESXi, you would have like the VI client, or you'd have Virtual Center, and that gives you the view into what's happening at the hardware level, and of course at the virtual machine level as well. So you're talking very much to the parts that are close to the hardware in many cases, because you need to see what's happening there.
I think an example might help. Let's say that I have an ESX server with 80 gigabytes of memory, and I want to create 10 VMs, each one with 8 gigabytes of memory. Then 80 divided by 8 is 10. But can I also create 20 virtual machines with 8 gigabytes of memory each? So although I am using 160 gigabytes, but they're all virtual, is it possible, or am I limited by 10 virtual machines?
Oh, I see. Okay. All right. So the question really is, can you use oversubscription? And yes, you certainly can use oversubscription. And the whole nature of virtualization, for the most part, revolves around the fact that you can oversubscribe. Typically, in a given environment, let's say those 3 virtual machines were each physical machine. So you had 3 different servers, and we can simply call them A, B, and C to not have to worry about what applications they're running or whatever it might be. But each of those servers might possibly have, let's say, 8 gigabytes of memory and have a 2 gigahertz processor and have a certain amount of storage. And they're running applications. But how busy are they? So you might look at server A, and you'll notice that although it has a 2 gigahertz processor, on average, you're only using, let's say, 500 megahertz of CPU cycles. So the CPU utilization is only 25%. So could I then take 3 systems that are working like that and put them on a single physical server with a 2 gigahertz processor? Yes, I could, because essentially I've taken 3 systems that are 25% utilized and put them onto one physical system, which will now be 75% utilized. So one of the advantages then is that I can oversubscribe, in the sense that if I said, well, I've got a total of 6 gigahertz worth of computing cycles, do I need 6 gigahertz for the actual server? And no, I don't. So I can oversubscribe. But obviously that oversubscription means that you need to know something about how those resources are being used. Because if I had 3 physical servers that were 100% utilized, then I could not. And so that's exactly where your example comes in. Yeah. I can certainly have the sum total of my individual servers add up to more than what I have available on the real host that I'll be using for virtualization, but not at the same time. Because that, of course, would mean that I run out of resources very quickly. Right, so again, part of the whole design process is going to be a very close look at what's happening in the current environment before we virtualize, in order to ensure that we do have enough resources available. Right, so what is the need for compute virtualization? Well, we've just been through a large part of that, and essentially it's to make more efficient use of the available resources. So if we look here, for example, there's a before and an after. One of the advantages we saw is that on a given physical host, you run one operating system at a time, whereas if you use that same hardware and you have virtual machines running on top of it, you could have more than one operating system. So that really makes it a lot more versatile. What else? Well, in the typical single machine, we have very closely coupled hardware and software. So you have, for example, a given, the example I used earlier was a disk drive. You have a given disk drive, you have a device driver for that disk drive, but that's very closely coupled to what the operating system sees. So on your machine, essentially the operating system knows this is the hardware that I have. And if I were to try and move that somewhere else, it might not behave in exactly the same way. So I can expect that the operating system would, but the device driver that I have on system A might not work on system B if I did a backup from here and a restore to there, because that doesn't have the XYZ brand disk drive anymore. It has an ABC, which behaves a little bit differently. So I couldn't easily move from one piece of hardware to another because of the differences in the hardware and the differences that are seen by the software. In the virtualized environment, essentially, what we have is a way of presenting to those virtual machines a common set of virtualized hardware. So instead of saying, well, I have, an XYZ brand hard drive, the virtual machines know that they have access to a generic hard drive. And it looks the same for every virtual machine. And it doesn't matter what the actual hardware is, because the virtualization layer is going to take care of that. So now I know that because my virtual machine sees essentially a consistent and common set of virtualized hardware, I can take this virtual machine and I can move it onto another host, even though that may have different physical hardware, but it will look exactly the same. The virtual machine just doesn't know because it is not tied to that physical hardware at all. So that's one of the advantages then of virtualization, is the fact that the virtual machines can be made portable. I can easily get them from one host to another host without a lot of additional work taking place. Also, of course, inside the virtualized environment, we go to great pains, or the software vendor goes to great pains to ensure that the virtual machines are kept separate from each other. So they obviously have access to common resources, but there's a very distinct barrier between what one system can access and what another system can access. So what we're trying to prevent here, of course, is data leakage from one system to another, or invalid or illegal access of one system to the data that is owned by another. And so we don't have then that conflict. We've isolated them very carefully. Also, the utilization was something that we just discussed a few minutes ago, but the goal here is to improve that resource utilization. So to make sure that it is kept running at close to maximum, or at least closer to maximum than a regular group of physical machines would be doing. And of course, those physical machines typically do not run anywhere near 100%, so we can easily do this. And of course, the other advantage is the flexibility. So as mentioned just a bit earlier, we do have the portability associated with those virtual machines and the ability to move them around very simply. And again, that's all because we virtualized the hardware. So the virtual machine itself doesn't know and doesn't care what hardware is actually there. Another area that's becoming increasingly important is the area of desktop virtualization. And once again, we have a definition here. So desktop virtualization, the technology that enables detachment of user state and the OS from endpoint devices. All right, so essentially when you log in somewhere and you're at your laptop, everything about your current state is local to you. So you're busy with an application, your laptop essentially knows exactly where you are. It knows how you want your screen to be configured. And all of those personalized type areas, do you want to single click on something to launch it, or do you want to have to double click? All of that information is local. So your laptop dies and you have to request a new one. Let's assume there was no backup or whatever of that state. So you get a new laptop, and now what do you have? Well, the screen background is not, your favorite picture of Fido. It's now, something generic. Your screensaver is not what you had before. You now have to double click to launch things instead of single click, and so on. Because what you had was tied to that local device. With desktop virtualization, you're still going to be accessing something through a local device of some sort. You have to have a keyboard and you have to have a screen and presumably a mouse as well. But that information, the information about you, the user state and so on, is not saved locally anymore. It is saved somewhere else. And you are presented with a view of all of that information in a virtualized type environment. So essentially here, you have PCs and thin clients. All right, so a thin client really doesn't have very much processing capability of its own or storage of its own, but it allows you to access through a regular network a group of virtual machines, desktop VMs, and your information then is saved there. So the advantage of this is essentially I can go anywhere and I can log in and access my information, and I'll see exactly what I had before, because it's not saved on the local device that I'm dealing with. And of course, again, when you're dealing with lots of local devices, how heavily utilized are they? Well, there are a whole bunch of laptops in the class right now. None of them even has the lid open, right? So they're not being used very efficiently. Not much is happening. But if this was virtualized, then the virtualization process itself, which would allow that oversubscription, would be able to say, well, there are 16 systems here that are doing essentially nothing, so they don't need resources. Those resources can be better utilized elsewhere. And that's exactly what would happen. So again, we're improving the efficiency by allowing that sharing of resources, a much better allocation of resources, plus, of course, again, making sure that your view is consistent. Your user state is consistent because it's kept somewhere else. Also, and really importantly, is the potential improvement in data security. All right, so you have, again, a local system. You have USB ports. You can connect a thumb drive to that. You can connect an external device to that. And you can take that information with you and go somewhere else. So you resign, you go to a competitor, you've got all of this information. You have sensitive emails or whatever saved right there. Maybe you lose your laptop. It's stolen out of your car or something like that. But that information is there and it's accessible. With the virtualization, the storage of that information is, again, not local. It's saved somewhere else. So you always have access to it, but you do not have the ability to take that information and use it in some unauthorized way. So it's a very secure environment. Yes?
With virtual desktops, is there a measure of the data that ends up being stored locally as well, kind of similar to how some memory is, or some data is stored on RAM for quick access and just improved performance? Is it the same thing with virtual desktops as well?
It could be, but typically it isn't. Because if you look at the types of systems you're using here, a thin client, by definition, is, well, not necessarily dumb. So we're not talking about a terminal where you limited to like text access only. But essentially, for a thin client, you really need nothing much beyond the ability to show graphics on a screen, to be able to accept input from a keyboard and mouse and send them through to somewhere, and a network connection to get you to where it is you're going to be sending them to. So you do not need any local storage at all, and typically, you wouldn't have. So all of the processing, everything really except for the input and output part will be performed somewhere else, and that will be at these virtual machines here. And the display to you and the input from keyboard and mouse will be local. But that's typically the way it would be implemented, yeah.
But you do need to be able to monitor and dynamically characterize each virtual machine, right? So you can reallocate resources to maximize utilization and efficiency, right?
Oh, absolutely, yeah. So obviously the hypervisor itself will be allocating resources as required, but it needs to keep a check on how they're being used, yes. Very much so. Yeah.
I understand that there's some global research projects and green energy type projects that are going on where they're asking to use personal computing power, and you can actually sign up to let them use your CPU or memory when you're not using it. Is that kind of like reverse virtualization, or is that virtualization? Or
okay, so
neither of the above.
So you're thinking of something like the SETI type thing, that search for. I suppose in a way that's almost like loosely coupled clustering of a sort, really, because you're breaking up a rather large job into very small pieces, and you're allocating those pieces out to individual machines. So I guess in a way it has some of the benefits maybe of virtualization, because you're able to increase the utilization of the individual local resource. So, when you're not typing away, something else is busy, causing the CPU to churn over. But I'm not sure that one would call it virtualization in the strict sense. Yeah.
More resource sharing.
Yeah.
I have a question regarding these thin clients.
Yeah.
They have no memory at all. I mean, they must have some kind of memory to interact with the network, and only they use the network buffers on the network card or something? Or they have some kind of memory? I mean, I understand the memory, the actual memory for the applications to run is going to be on the VMs, or on the cloud or something, on the data center.
Yeah.
But these thin clients must have some sort of memory, no?
Well, yeah, any computer system will have memory, and that, of course, is a computer system, because it does have, the input and output associated with, a normal computer system and the CPU involved. But the memory that you need there is largely to support the connectivity to and from where the actual application runs, and memory to support the display of graphics locally. It's run elsewhere, yeah. So all of your user information and the work that you're performing is being performed somewhere else, yeah. So I guess in a sense, if you perform like a remote desktop connection to another Windows host and you run something there, that's pretty much the same type of thing, because right now all you're using your local system for is to do the display and receive keyboard and mouse input, but the work's all being done somewhere else. Yeah.
Sorry, one more question. So where are we I kind of see like thin clients as being kind of like the nirvana of virtualization, right? Like this is kind of the end goal of being able to do that. Where are we at in the adoption curve of actually being able to implement, in large corporations, thin clients or other use cases?
Well, I don't have exact numbers. I do know, though, that it is becoming a lot more popular and adopted a lot more frequently. So some of the solutions that we looked at in the VNX environment, for example, used VDI as one of the sort of examples to show where that technology can be used more efficiently. So if it wasn't popular, if it was something that wasn't being adopted fairly frequently, then it would never have made it that far. So certainly it is something that that companies are looking at, and I know even inside EMC we do have, I'm not part of the program, but there is a program using virtual desktops. So certainly I think it's an end goal that a lot of companies have, but how quickly they get there, depends on a number of different factors. Yeah. Right, so that was desktop virtualization, and that brings us to the end of the first lesson.